My recording. Yep. Sorry for that.
Okay, continue. Okay. So to talk about the central monads, we use the strong monads. The strong monads, they are combining effects and pairing with the special structure strengths. So we can use the tau here to make the T out of it. And in the computational way, we have the pair. We always return with a pair. And there is it was found in the 1997 by Tao and Robertson that a premonoidal category P has a center. Which the premonoidal category is where the tensor is not a bifunctor, but it has a center which is a monoidal subcategory, which the tensor is a bifunctor. And comes from that, we have another thing that the Klesley category of a strong monad is a premonoidal category. Then that's we actually from the paper of the center of monads, they discovered the connection with the center of the premonoidal category to their construction of the center of the monad. Doesn't work. Just click it. Okay. Yeah. To formally construct such a center of the monad, they define a structure called the central cone, which actually first you don't need to look at the whole picture. We only need to look at this picture. It's actually the commutativity of the monad. We first apply the co-strengths and we apply the strengths. It will be equal to apply with the strengths and co-strengths, and for every x and y. But a central cone of the monad T at x is given by a pair Z and the iota, which the iota here is the morphism between monads. It's a morphism from Z to the T of x, which makes the diagram commute. So from that, they have they discovered the connection with that they discover that if there exists universal central cones, it actually is equivalent to that there is a commutative monad such that the Klesley category of the Z is equal to the center of the Klesley category of the monad. And also the third one is with the adjoint thing. And their proof strategy is that all the morphisms, the morphism indicates the morphism here between the monads, the iota here. The all morphisms are central in the premonoidal category sense. So, but they didn't give the direct construction on the monadic structure. But I mean, this is a good theorem because it's a universal property. And they from this centralizability, they can say that if they satisfy any one of the conditions, we can say that a strong monad is centralizable. And from the centralizable, they induce the center of one monad. So if we look at some examples, for example, if we already have a commutative monad, the center should be itself because it commutes with every other elements. And just move one step forward. If we have a right monad induced by a monoid n, which the n has a center C of n, the monad is this way, and the center is just the right monad induced by the monoid Cn. So as you can see that actually it's not quite interesting applications. I mean, first they came to me to solve with the internship was also to find more examples of central monads because they discovered that for many category which has a clear sub-object, for example, in the category of sets, in the category of tops, they naturally have a center and is normally just the identity or a constant one. So it's not so interesting. So one step forward, we are thinking of how can we make it like more interesting in applications. we are thinking of moving the center of monad to a graded monads. Because if we use the graded monads, graded monads is just a generalization of monads. In the way of, we can just consider the normal monad as a graded monad graded by a terminal object. And why we use the pomonoids? Like we use the gradation especially as a pomonoid because the process structure is especially interesting in the computations. Like normally, if we have a pomonoid, it's more interesting. And here is the definition of a pomonoid graded monad. So first we have for every elements in the gradation, the G we call the gradation, we have an interfunctor T of A, and also we have the eta just like the normal monad. We have the mu just like graded monad, and especially for the pomonoid structure, for any of this relation here, if we exist A smaller or equal to A prime in the gradation, there exists a natural transformation T such that goes from the T of A to T of A prime, or with all the commutative diagrams. This structure is especially interesting. I will introduce it later why it's very interesting. And I mean, in the overview of we come from monad, which is interfunctor over the category C, to a lax monoidal functor from the pomonoid, which is gradation, to the interfunctor category of C. So like it's from this point of view, it's not the same structure anymore. So moving from the center of monad to the center of graded monad, we also need to construct a similar structure, which is the graded central cone here. But as you can probably recall here, to construct such a central cone, we have to define such a morphism between the graded monads. Hence, we have to work on the morphism between the pomonoid graded strong monads. And this, I should say, it takes much of time, at least for me, because it was very difficult for me. So a morphism between them, in the overview, is we have one graded monad here, is from the gradation, which is the pomonoid G here, and another gradation is the pomonoid H here. And this lax monoidal functor is the first graded monad, and this lax monoidal functor is the second graded monad. And this is the phi, which is the homomorphism. No, it's the morphism between the two gradations. And this iota is the morphism we need to define. And here I give you the details of the definition and why this relation is this transformation is interesting. So wait. So yes. So to define the morphism, we need to define three kinds of morphism. One is the eta, one is the mu, and the other one is the strength tau. But I mean, we can just ignore both of them. I just focus on explaining this little diagram here. So if we come from X, we first have eta come from X, eta from the first graded monad T. We apply the eta, we have the T of I here, and we apply the another eta of the pomonoid P, the graded monad P. We have the P of E here, and if we apply the morphism iota here, it comes from the T of I goes to the P of phi of I. Then the question is, how do we define the relation between P of E to the P of phi of I? Then interesting thing is we exactly have this kind of relation in the gradation. So in the pomonoid morphism, we do have such a relation. The identity of the first pomonoid E should be less than equal than I, or I less than equal to E, yes. So we if we have this relation in the morphism, then by the definition, there is a natural transformation between them. So then we can have this arrow here. And similar, in the mu, we apply all of them. We also have this relation is between the P of Phi big star Pb to the P of Phi of A star B. And actually, like this definition is like stronger than we thought, because this is only defined on the permanently graded strong monads. If we discard the permonoid, actually it works on any kind of like Lex monoid functors. If there is a morphism between them, between the gradations, and if there is a relation between them, we can define such an arrow, so that we can have this morphism. So from this morphism, we can now define the graded central cone, which is at z, and the x is given by a pair z and the iota, which is the iota here is the new morphism between graded strong monads. And the rest of the, similar to the non-graded version, the rest of the diagram is the commutative property of graded monad. And we defined the graded central cone start from here, from there. And but from this construction, we didn't have the universal property of the normal monad. If we go back to the normal monad, they have a theorem which states that those three kind of conditions are equal. Both all of them are centralizable. But from the graded version, we only have this. It's kind of like we claimed it. Like we claim if the terminal central cone exists, it's centralizable. The reason we don't have a universal property yet is because that we haven't investigated through the classic construction. It's actually really complicated. And another reason is that there is no study at least from our understanding yet of the graded version of the premonoidal center. So this is the only thing we defined, like for the center of graded monads. And of course, if it's centralizable, we can define the commutative graded submonad as a center. But as you can see, we do not anymore have a premonoidal center. The construction of this centralizability has to come from a direct construction of the monadic structure. More specifically, we have to prove that all of the morphisms, they construct a terminal central cone. And this proof strategy is very different from the original proof. And also, of course, it works on the non-graded version too. And yeah, we don't have anything regarding to the graded premonoidal center and the classicity construction. And I don't personally, I don't even think that we should go this way, because we construct this from the scratch. We don't need like probably go classy, but I don't think we need to go that direction. And after this definition, we are trying to find some the application of the center of graded monads, because the first intuition about this is like we are trying to find more interesting examples, but I have to say we failed to find it, because the way we construct this center is that the morphism, you can see the morphism here is not anymore that there is a morphism between the gradations. We simply take the subset inclusion. So the gradation of the center is just a subset of the gradation of the original graded monad. So it's not so interesting anymore. It's just subsets. So actually, it's simply making the monad more explicit, and we are simply checking the effects. For example, we have this example here. We suppose T is a normal strong monad, and Z is the center of the normal strong monad. So then we can construct a graded monad by this kind of homoloid with Boolean, and the identity is true. We have a relation here, and this is n. So that if we have if the is in the center, we grade it by the truth value. If it's not, we grade it by the false. So we have the morphism here as the subset inclusion. So then this example shows the very limited application power of the grading monad. We center of grading monad we define is that it only checks whether the effects an effects operation can be evaluated in an order independent manner. More specifically, it doesn't care you evaluate the order, like you can evaluate TA first or TB first. It doesn't affect the results. But as you can see, it just makes the original center more explicit. There's nothing very interesting about it. So moving forward, we are trying to say also what we can do to jump out of it, to make it more powerful. And yeah, there are three directions we considered. The first is that out of the question of the applications, you can try to define the center of monads. The gradation of the center can be, instead of just the subset inclusion, can be something homomorphic to the center of the gradation. Then it becomes more interesting because there are more structures inside. It's not simply an inclusion. We can use the full power of the morphism we define. And the second way is like we can actually go graded premonodal center and find the universal property to construct the center on graded classic construction, which which I don't really like this idea because I give an example for like we have a orange and we have a clementine. We find that this kind of orange tastes just like the clementine, and now we roasted the orange. I mean, this is a new flavor. We don't need to roast the clementine and claim that, oh, the roasted orange tastes just like the roasted clementines. It's absurd. And third way is what we did is to relax the commutativity of grading monads to border the application power. And to do that, we introduced the duet as gradation. The duet is half sequential and half parallel, which the second parallel structure is for the commutativity, and sequential is doing the commutations. And I give you the definition here. The lax commutative, it doesn't rely on the tau anymore. It just extracts all the t, both of the t, and yeah, take it out. And this is the definition of a duet. What makes it especially interesting is the unequivalent here. That's we can use for duet graded monads, which we suppose that it should be interesting. But given the time, we only have 4 months. We don't have any real example yet. This is what we are trying to work on, and that's it. Thank you.
So where did this idea of grading come from? What application was motivated that?
Yeah, it was actually brought out by Flavian. So he was working on graded monads, and he was thinking that there should be something interesting, like his example is just this example, like make it more explicit. We were like considering more complicated examples, but wait, where is it? Well, yes, we were considering more complex examples. For example, involving like distributive laws, but we wasn't sure that the result could be positive.
You had some on, I think, second from the last slide. You had what looked like the interchange law of two categories.
Which slide?
About 2 slides from the end.
Which
Go,
one?
go to the end and then go backwards. Here, that looked a bit like the interchange law.
Yeah.
If two categories.
Yes, but we didn't have enough time to investigate on it. It was just we simply gave the definitions and say that it can be useful.
Yes, so do you mind getting back to that definition of like the graded monads? It's a lux, like,
Yes.
Yeah. So there's like, I guess a slight like horizontal application you could do, which is consider instead a lax monoidal bifunctor from a plane monoid considered as a one object bicategory into the bicategory categories. And so then you wouldn't just have n function anymore, but like functors more generally. And I was wondering, can you think of any reason why your results wouldn't apply in this more general kind of setting?
I think so. First, I'm not really sure about that, but I think the thing is that we define this morphism, which is good, but the center we define is like we simply take the subset inclusion. Like we haven't been able to consider more complex scenarios, but it should be done though. Yeah.
Okay, well, let's thank Mr. Ron for his talk.
Well, we can set up very slowly. So Alois is next. Yeah, well, I guess you can pull on a 5-minute stand-up routine if you'd like. It's there. I'm still recording. Just give it a couple minutes, just in case someone's tuning in just for you.
Yeah.
Would anyone be tuning in just for you?
I think my co-author Micah.
Ah, there you go. So I might come up here. We'll see you. Micah's here. Micah's here. I'm two.
Where's the microphone for the
microphone
recording?
is there.
Okay.
Actually, what I will do in the meantime, I will mute my emails because they were. Oh, but they've also now been put on the stream as well. Great. So I've lost our. So I heard an email come in. Hi, over to me. As I will slowly.
Yeah, perfect. Thank you. This is for the pointer.
It's the red one. Those are lights, yeah.
Perfect,
Sure.
thank you.
As I will walk slowly across the small time.
Are we waiting for anybody in particular?
Hmm?
Are we waiting for anybody in
No,
particular
no.
online? Let's get going then. So this is Owen's Rotte from where are you from? Amsterdam. Who's going to tell us about composite theories and distribution laws, a subject that goes back to John Beck.
Yeah, exactly. Thank you very much. So this is joint work with Micah and my two supervisor, Alain Jot. And so let me start with, in one slide, try to explain to you an overview of what I did. And if there's one thing you need to take away from this presentation, this is it. So as most of you probably know, there is a correspondence between finite monads and algebraic theories. And also another correspondence has been expressed lately, a few years ago, between distributive laws and something called composite theories. This correspondence was first explored by Chang on the level of Lavery theories, and then translated to how it should correspond for algebraic theories by Pierre Staton. And this correspondence was what allowed Micah to express her famous no-go theorems for distributive laws. So with this setup, I was wondering, wow, we have distributive laws, and nowadays there is another notion that has gained traction, which is called weak distributive laws. I was wondering, could I extend this correspondence to the weak setting? So that was my setup. So I thought I would dive into this first correspondence to try to understand fully and then translate it. And I realized that it was only one part of this correspondence was in fact fully proven. So I decided to finish it And then when I realized that was quite some pages, I contacted Mike, and we made a paper together with both half-truths. So this is the setup. I've included a slide on monads, but I guess most of you are probably familiar with what those are. Here are two examples of monad, like the list monad or process monad for non-determined. For monads, there is notion of monad algebra, and in this talk we could talk a lot about distributive laws. So for those of you that have never heard of it, indeed it goes back to Beck. And the prime example of a distributive law is the fact that this multiplication distribute over addition, right? This was like a categorification of that fact expressed through monads, with the two monads being present for multiplication and addition are monoid, so the list monad for monoid, and the Billion group monad. On the other side of this first correspondence, there is algebraic theory. So most of you are also familiar with it. Just to write notation, I will write arities of function symbols in superscript. For every algebraic theory, there's also a notion of algebras where it's an interpretation that satisfies all equations. And for every algebraic theory, there is a free forgetful adjunction where we take the equivalence classes of terms. And if we compose this adjunction, we get a monad called the free algebra monad. And this allows for this first correspondence that I mentioned about. An algebraic theory is a presentation of a monad if we have an isomorphism of monads, or equivalently an isomorphism between the category of algebras. Right. So this first isomorphism relates the two monads on a syntactic level, and the second one on the semantic level. And yeah, right, this is something that we usually do where we consider equivalently a list as a monoid term and cert as a join as a lattice term, etc. Right. So this is the setup, but there is one more preliminary that I need for that I've used in this paper, which is term rewriting. So I don't know this one you're familiar with. So let me just have one slide. So there is two types of rewriting that I will use, which is called string rewriting and term rewriting, where the first one can be seen as like a special case of term rewriting where every function symbol has an arity 1. And so a string rewriting or term rewriting is just a set of rules with the left-hand side and right-hand side. And when we have such a rewriting system, there's three properties that we're usually interested in. Those three properties are termination, tells you that every rewrite sequence terminates. And the two others are two variations of something called confluence, which one local version and then a global version. In the local version, you ask that if you start with the term and have two distinct rules applied, then you might rejoin them. And when I write this double head arrow, it means the reflexive and transitive closure, so 0, 1 or more steps. So here local is when you do one step peak, and the confluence is when you have multiple steps. And the reason why we care about those properties in particular is that when you have both termination and confluence, you have something called normal forms. A normal form is a term that cannot be rewritten anymore. And termination tells you that those normal forms exist, and confluence tells you that they are unique. And so computationally, it's very interesting. And here are like two main results that tell you how to derive those properties. So confluence is very hard sometimes to calculate, to know if it exists, but thankfully there is the Newman's lemma that tells you that if you have termination, then local confluence is enough to entail global confluence. And to know if weak local confluence holds, there is a nice criteria, which is we have something called critical pairs, which are basically all the culprits where local confluence could fail. So it's all the times where two rules overlap with only symbol, like here, A, B, and B, C. And in that example, so this is the string rewriting system here. In that example, this is not confluent because here this critical pair doesn't converge. You cannot join them at the bottom. So this is some preliminary on graph rewriting. So now let me tell you the other side. So this is what the preliminaries. Now tell me the other side of distributive laws. Distributive laws are well known, but maybe you have never seen composite theory. So let me flesh it out. In the same way that the basic distributive law is multiplication over addition, on the other side, this will be the same thing with the theories. And in fact, it corresponds to the theory of the monoid abelian groups. Then when you put them together, you obtain the theory of rings. And the theory of rings is both theories plus two distributivity axioms, right? Left and right distributivity. And composite theories is like the axiomatization of this behavior of what we have here. And so basically, thanks to left and right distributivity, every time you have a ring term, you can just distribute everything and always end up with an abelian group term with inside his the variable substituted for a monoid. So when we put that into a definition, if you have two theories S and T contained in a bigger theory U, we say that the term is separated if it's of this form, so a T term with S terms inside. So here the notation X means that X ranges over all the variables in T. And when we have two separated terms, we say they are equal modulo ST if they are essentially unique, in the sense that if we take their equivalence classes in TS, so remember, so those are the free algebra monads, so now we work with equivalence classes, that their TS equivalence classes are equal. And what this means is that we can basically compare the two separated terms on the two levels, like on the T level and the S level. And this allows us to have the definition that the composite theory is a theory where every term is separated, can be separated, so I mean at least one separation. And if you have two of them, two separations, they must be essentially unique, so they must be equal modulo ST.
So this is like multiplication being the inside thing and addition being the outside.
Exactly. Yeah. Exactly. And indeed, in ring, right? In ring, we have this equality that 0 is the same thing as 1 times x minus x times 1. But more than just this equality in ring, we have that this equality, in fact, falls on the two levels, right? X minus x equals 0 and x times 1 equals 1 times x. So now we have that we have everything.
We're back. And
Amazing PDF.
yes, but I need to make it the full screen one. So it's this one. And that's the wrong thing. And it's the, or maybe it's that one.
Nice.
And there, and then still, no streams are going. Recording is happening, I think. Top calling, yep, cool. Then I'm sure. I'm back. I'm back.
Cool. We're back. This was the ad break. So in that direction, when we start with the composite theory, we can build a distributive law that, given the term in SC, just take the representative and give the separation of it. And this is well defined because of this equality modulo ST, because of this essential uniqueness. And checking that this is a distributive law is just tedious but straightforward. So that was the existing direction. Now the other one, suppose we start with the distributive law. We need to now build a composite theory. So how do we do that? We just join both theories, but we add like this third set of of equations, which are the distributivity equations. So how are those defined? It's every pair of terms that are representative of an input and output of lambda, of a distributive mode. And with that defined, then we claim that the lambda is a composite theory of TNS, TFS. And we tried first to prove the thing like directly by hands with induction on terms and induction on the proof tree to prove both properties of the composite theory. But that's where we hurt ourselves and realized that some graph rewriting was much needed. So let me show you the tools that we need from rewriting to have this proof. So first of all, given the u lambda term, we have defined in the first function, which is what we call type, that gives the string of term a string in this set made of letters S and T's that tells you how nested the operations are, right? So you have like S terms and S operations and T operations and S operations, etc. So in that case where we have F being S terms and G being T terms, and that u lambda term with some coloring, we realize that the type is STS, so blue, right, blue, green, blue. And then we introduce also this notation where we write the type of it. We take the equivalence class to mean when we put the equivalence class bar at the right place every time. So we only use this notation when it's unambiguous, of course. And the idea is that given the term u, to separate it, we first look at it in its equivalence class, and then we apply all three natural transformation as much as we can until we reach a point where it's no longer possible, being either TS, T, or just S. And this really resembles rewriting with the normal form, right? So we've defined, we have given it a name called functor rewriting system that appeared in some form or in the literature under the name rewrite category. But the functor rewriting system is just the alphabet are functors and the rules are natural transformations. And we take the functors just as like strings of alphabet. So if there is an equality between functors, we don't allow it. And like, so we have one in our case, right? The letters are S and T's, and the three rules that we consider are lambda and the both multiplications. And why do we give it a special name? Is because now we're like, with functors and natural transformation, there is one more data that we can make use of, which are when diagrams commute. So we give those two variations of confluence where we add like the word commuting afterwards, and this represented also by this little arrow and circle arrow. So when the same diagram has confluence as before, but the same thing with the commuting diagram. And both results that hold for term rewriting systems also hold in this setting. So when you have termination and local confluence commuting, you have confluence commuting, and to have local confluence commuting, it suffices to look at critical pairs. And with that done, like our system that we have, it's a bit straightforward to check that it's both terminating and confluence commuting. For termination, any technique that you like, we choose polynomial interpretation, where we can give a higher weight on the S letter than on the T letters, and then every rule being strictly decreasing this ensure termination because N is well founded. And for local confluence, there is exactly 4 critical pairs that we need to consider, which are those 4, which are exactly the axioms of lambda and of monads. So it's really funny how like this was very natural to consider. It's really funny to you've probably all noticed that like a lot of very often category theory axioms even make sense from a purely like rewriting point of view, right? If you are an SST and want to find 2 ways to end up in TS, there's those 2 natural ways, and you ask them to commute. So yeah, this proves it's terminating and confluence commuting. And now that we have that, we can take define a function that's separated, that separate any u lambda term, where we take the equivalence class and take any path to normal form, because we know that we know that those are equal. And once we are in the normal form, just take any representative of it. And this way you have the first part, which is that every u lambda term can be separated. But we have more than that. We have not like any path to normal form are equal. And this is useful for the second part, which is that if you have 2 separated terms, then we ask that are equal, they must also be equal modulo ST. And now that we have all these tools, the proof is tedious, but just again straightforward, where we do an induction on the proof tree, and we prove that like at every step, at every equality, we just separate both sides with our function set, and we have equality modulo ST. So every study is straightforward. those are like the complex cases, but again, just it follows by this sequence of equalities. The annoying part without these tools of rewriting was the transitivity case, because if you started, if you try to do the proof without rewriting, you were like, okay, I want to do an induction of the proof tree, and at every level, I want to prove that the equality modulo ST is preserved. So the problem is that you could go from U1, which is separated, to U2, which may be unseparated. Like if you have an equality of separated elements, U1 go U3, U2 might be not. And if you're like, okay, I separate every level, you might separate U2 differently in both branches, right? Here above and here above. But now this is straightforward. So that was it for the proof of this correspondence. There is one last result, which is that in both directions, we have that the composite monad given by the distributive law is presented by this composite theory. And in this direction, there was also a proof in Swart's thesis, but we just updated it with a shortcut that maybe some of you know. This notion of lambda algebras. When you have a distributive law, it's something that is both like a triple, which is both an S algebra and a T algebra. And this theorem, we'll look at it a little bit more, because it tells us that if we have a distributive law, it's usually distributive laws are useful because it's a sufficient criteria to know that the monad's composed, right? And this theorem tells you that, okay, if you have that, we already have even a presentation of that monad. But there is just a slight problem. U lambda, as it was defined, was nice for the correspondent theorem because it contained all distributive equations. But in practice, we don't want infinitely many of them, right? So we want to find a minimal axiomatization of U lambda that is that has the same congruence generated as in U lambda, right? In the basic example of multiplication of right, if we were to start with the distributive law lambda and construct U lambda, we would contain all those distributive equations, right? Even like basic one as x equals x or x equals x plus 0. And we have expressed a way to determine to showcase minimal sets when a minimal set can be served as a minimal axiomatization. To do that, they just employ some terminology of layers. So if we have a term which is made of an S part and a T part, the layers is a pair of natural numbers where it's the number of operations. So the number of S operation and the maximum of the number of T operations. So visually, if you write a tree, if you write a term as a tree, it's really the number of layers that you have visually. So for example, here, that term has a 1-1 because it's one multiplication operation with every subterm being one abelian group operation, and here it's layer 0, 2 first. And what this allows us is those two lemmas that give us this minimal representation. So we consider only the equations that have left-hand side of this shape, where it's one S operation with inside only one of the arguments being not a variable and being exactly one T operation. And for the right-hand side, we just pick one of them. And this is a term rewriting system. And if this is terminating, then we have the same congruence. So this was the first result that we obtained, that if it's terminating. So now here is a second lemma that tells us one type of scenario where this termination is ensured. So if all the rules are of this form, so left-hand side has layers 1, 1, and the right-hand side has layers something 1, and some linearity requirements, then we have termination. And let me show you 3 examples where we have this setup applying. So in the case of lambda of the multiplication of addition, this holds. So this is how we end up with only left and right distributive equations. But also many other in the literature that we checked. So here are 3 examples that we picked out of randomly. And in every case, we obtain a very elegant axiomatization of the composite monad. But just consider indeed only equations that have a left-hand side of layers 1, 1, right? So only one operation of each theory. And right, this would be the way that people usually sometimes even define distributive laws, right? You just look at the algebraic side, just write one distributivity equation and say, ah, we have a distributive law. But this is something very dangerous to do, right? Even though it's tempting, and this has resulted in many of the errors in literature about wrong distributive laws. So this is a small setting that tells us sometimes we can do it, but we have to be careful. And some comment about the criteria that we have found. If it's terminating, then we have the same congruence. Here is a small example that tells you that it's not always the case. Like that if termination is not there, then the conclusion might fail. So this is a quick counterexample that is built upon one of the famous, like a basic exercise when you have a TRS class, which is that if you have a single rule A B goes to BAA, this is a non-terminating TRS. The reasoning being that if you start on AAB, then you are stuck in a loop. And we just realized that we could extend a little bit that counterexample, that TRS, to obtain a counterexample that shows that this gives a distributive law. We have adapted it to obtain a distributive law. And if we only take the equations, the distributivity equations with left-hand side layers 1, 1, then there is one distributivity equations that we cannot derive. So this showcases how, why termination might be important. But I'm not going to go too much into the detail of what distributive law is. Just an extension of that can be wrong. So that was enough for my presentation. In summary, now we have a fully fledged, full proof of this correspondence in the category of sets between distributive laws and composite theories. And what was really interesting, I found, was the proof strategy that we came up with. And then we gave a criteria when a minimal axiomatization can work. And for future work, there is, of course, we give one example of when this termination is unsure, so we can look for more criteria. But nowadays, all distributive laws that we have gathered fall under the one termination scenario that we've expressed. But we can now that this correspondence has a full proof, we can look at how to extend the correspondence. For instance, like what I said in the intro, work on weak distributive laws. But there is also make sure that everything works when we add non-finite monads. So if you know this is on the algebraic side, it's when you allow function symbols to have infinite arities. In the case, a main example being, for instance, the power set monad or the ultra-filter monad. We can change the base category set. This is kind of difficult to do. Some people work on monads, not on sets. There are many examples of that. But very, very quickly, if you try to change the base category, you very quickly end up working with Lavery theories. And just like the original correspondence that was on the level of Lavery theories. And this is very more obscure what's happening, which is the nice aspect of this correspondence in set. So there is weak distributive laws that are worth looking at, or also when you have not only one sort, so multi-sorted algebraic theories, what happened there. So these are full leads for extending the correspondence further. The one I'm mostly interested in is the one that I started with, so in the weak setting. But that's it. Thank you for your attention. Yeah, that was my presentation.
You're both fluent in both the diagrammatic and the symbolic ways of seeing algebra. Very good. There was many years ago, there were some semi-Russian people who were using categories. I hadn't heard of them for a long time because of the fragmentation that happens in the algebra in the academic world, but it might be worthwhile trying to
do you know
find out.
Do you remember one of the author?
I'll think about it.
So the danger is that if you look rewriting and category theory, there is also an extension of term rewriting, which is graph rewriting.
Yes.
And nowadays, graph rewriting is done almost entirely in category theory. So most results you will find is about this framework, and that's also something that I've been working on.
One criticism, right?
Yeah.
You have Greek on your sweatshirt.
Yes.
The singular of criteria is criterion.
Sorry. Yeah. Thank you. Yes.
I have maybe a naive question, but concerning the concept of composite series.
Yes.
Can you represent say group rings of the composite theory?
Yeah, that's
so what twice you need to propose twice.
What do you mean by complex-wise?
You mean you start with groups and groups, so you create your rings, and then you compose again this group to get group rings.
Oh, I've never heard of group rings.
So actually, this you consider linear combination of group elements with coefficient being formally ring element,
Ah, yeah.
and then you organize a natural ring.
Yeah, that might be a composite theory. Do you have distributive equations in that case?
Yeah, yeah.
Okay, then yeah, that might be a perfect candidate for a composite theory.
Bit where you extended Newman's number and forget what the other one was called, to this functor rewriting system. Is that like a trivial extension, or is that something you want to go on?
No, it's very straightforward. It's basically looking at the proof of Newman's lemma and realizing that the proof is like can be summarized in one diagram. In fact, every part of the diagram commutes. Yes.
There's a notion of a theoretic cumulative theory, and it is where the function symbols they kind of commute in the sense. But then you can have one theory that commutes with another theory, in the sense that you can have take these terms from each set of these kind of terms, I mean function symbols, and then you have equations that kind of, so how much does this relate to this notion of distributivity law, that you have this kind of commutation between the function symbols? I know, of course, will be many variables.
How different?
So how is there a kind of a
I'm not sure.
connection?
I'm not sure to see what you are talking about. You're talking about when you just can commute the symbols.
That's it. I mean that okay, you will have a matrix amount of variables x, I, j's, and then you have a so if you have in one signature you have a function symbol if, and in the other signature you will have a function symbol g, and then you apply fg to the matrix, and then you have gf to the matrix, and to be accommodative means that these end results should be so I'm wondering if this is related to this, but
probably
The category theory is related to the buffer to the previous law. I think the category theory associated is the kind of mutually strong related.
yeah, that's.
But in which setting? So you work when you work with matrices, you've seen that that thing?
So we can talk about this.
Yeah.
So when you are writing these finding critical function,
Yes.
you had only monad multiplication law.
Yeah.
But somehow these unit laws are in I don't know how they are in because when you go to decompose, just to drop one of the unit laws, right?
Say we only we don't consider without either of those because in fact separating the term can be only done by swapping every instance of S and T in the wrong order, and then we have the tower of S and tower of T and shrinking it. There might be an interest in consider an older writing system where we have the units, but then of course we would lose termination because you can add symbols now instantly in time. Because then maybe it may be interesting in another way.
These functor rewriting systems.
Yes.
Can they be used to like reverse engineer? Can they kind of suppose you have some functors in that information structure? Can you kind of reverse engineer what coherence conditions are sensible ones by demanding like the nice properties of the functor rewriting system?
Well, I'm not sure to see what you mean by reverse engineering.
I suppose you have some structure, and you expect that there might be some natural coherence associated with the structure, functor and natural transformations.
Okay, some equality between natural transformations.
Yeah, right.
Yeah.
Like, can these be reverse engineered? Like, does the fact that like if you command that there is, that these make a functor rewriting system that has all the properties that you spoke about to somehow give you covariance solution.
So whenever you have a system with functors and distributed flows, natural transformations, and you have some equalities between the natural transformation at hand, you can transform that into a rewriting system. And the interest of it is a bit like one major application of TRS, of term rewriting systems, is to decide, it's to work when you have equational, it's called equational reasoning, but it's equational theories, algebraic theories. So to know how if a certain equality is derived, you can just compute both normal forms if they exist, and that gives you the equality. There is a correspondence between equality in equational reasoning and convertibility in the rewriting system. So you might have the same thing in any setting that you want in natural transformations, and you just put your equality that you start with, and you can maybe automatically deduce some theorems.
But related, by the way, how mapping moves the covariance theorem on systems system that so it's related. These systems are related to covariance.
Oh, didn't know. Thank you. Very good. Now,
Otherwise, an excellent talk. And you ready?
Yeah, okay. Yeah, so it's like that.
Down this forward.
Yeah. Okay, move down the top.
This is the bit that you think the pronunciation there. So this is Adrian Matteo from Edinburgh, who's going to tell us how to push on those.
Hello, everybody. Thanks to the organizers for giving me the opportunity to speak here. And indeed, yeah, today I wanted to talk about this construction of pushing a monad forward along a functor, which is really old. I mean, I think it first appeared in the formal theory of monads by Ross Street. But since, people haven't been talking about it, so I thought I'd do it today. So first, I'll introduce the concept of push forward monads, and then I'm just going to give you a bunch of examples, see if we can figure out what these things are and how they. In particular, I'm going to be looking at pushing monads forward from finite sets to sets, and then, so there's the word codensity monad there, which is going to be reached to push forward once as well, and we're going to look at the codensity monad. So okay, this is the basic situation that we're going to consider. We have a monad T in a category C, and we have a functor G going to some other category. Under what conditions can I take this monad T and this functor and produce a monad on the category? So the old answer, which goes back to, I guess, Huber and like the relation between adjunctions and monads, is that if G has a left adjoint, then I can get a monad on D by precomposing with a left adjoint and then the right adjoint. So I get a monad G and TF, and that's going to be a monad on D. If you're not used to this with a monad T in the middle, you can just take T to be the identity monad, and then we just get GF, which is the monad induced by the adjunction F. Now, the less known answer is that actually you can do this even when G doesn't have a left adjoint, provided that a certain can extension exists. And this is what's going to be what we're going to call the push forward of T along G. So let's see what this can extension is going to be. So I'm going to consider the following diagram. I have my monad T here on the left. I'm going to write my functor G twice. Okay, so I can try to extend this bottom composite along G above. And if that exists, it's going to give me a functor here, this right-hand extension. And as usual, right-hand extensions come with comparison, natural transformation in there. Now I claim that whenever this exists, it's going to have a monad structure, and it's what's going to be called the push forward. And I'm going to use this notation of G sub star T for this push forward. So I'm claiming this comes with monad structure, and then I will quickly describe it now. So this, the usual phrase is like a monad is a monad in the category of endofunctors. This one's going to be a monoid in a slightly modified category of endofunctors, which I've once I forget the modifications, it's just going to be with the monad. What this category is going to be, I'm going to call it KGT. Its objects are going to be pairs of an endofunctor of D and a natural transformation filling this square. And then a morphism is just going to be a natural transformation between the endofunctors alpha, such that when I glue it, I get what you'd expect. This is the question here. Now this category here, I've said it's monoidal. Let me tell you what the monoidal product is. So if I have two such pairs, S and S prime with sigma and sigma prime, which are these two squares here, I can compose them as such. So I put the two squares one on top of the other. That's not quite an element of the category because it doesn't go to T, but because T was originally a monad, I can then put on the multiplication here to go down to T, and I get a new object. And this one here is going to be the unit in this monoidal category, which is just the identity functor in D. This equality here in the middle, that doesn't quite go to T, but I can use the fact that I have a unit for the monad to put there. Okay, so I have a monoidal category, and I have one object, which is that right-hand extension. But if you look closely, the universal property of that right-hand extension is that it is the terminal object in this category of squares. And as any terminal object in a monoidal category, it has a unique monoid structure. So it's going to make this right-hand extension a monad because it's a monoid in this category of endofunctors. And so the composition is the same as the old one, except that we have to worry about. Okay, so that gives this G star T a canonical monad structure. Let's try to reconcile this with the old story I told, which is the old one about the adjunction. Turns out you do get the same thing. So if I happen to start with a functor G that has a left adjoint and monad T, then extending it using this right-hand extension business is going to give me the same thing as extending it knowing that it has a left. The proof of that is really, really simple. It's just a basic fact about right-hand extensions, is that whenever you right-hand extend along a right adjoint, you can compute that by just precomposing with the left. So indeed, we get that right-hand extension is monad induced by the adjunction. So let's see the most basic examples you can think of. For that, I'm going to sort of recall the basic formula for a right-hand extension, at least the pointwise one, at the limit. So here I'm right-hand extending GT along G. If I evaluate that on an object D of the category D, this is the formula for the limit. And here I'm indexing over the comma category D arrow G. So its objects are maps from D to G of some little c, and then morphisms are triangles, as you show in the comma category. And so this limit is going to give me the formula of the right-hand extension. So as I promised, here are the most simple examples you can think of. Let's see. So if I take the initial category, which is empty and has no objects or morphisms, and I take the unique functor from it to some other category D, I'm just going to require that category have a terminal object. Then the extension of the only monad on the initial category, which is the identity monad, is going to be constant at the terminal object, and that comes with a unique monad structure. And indeed, I mean, you can just look at the formula here. The indexing category is going to be empty, so it's an empty limit, and it is just going to be terminal objects. Okay, not super interesting. I did promise these are these examples. Here's one that's marginally more interesting. So now let me take the next most interesting category, least interesting category after the initial one, which is the terminal one object and one morphism. So a functor from it to another category D is just picking out an object. And if I require that that category have powers, so set index powers, then the extension, this is type, it should be D. The extension of the identity monad on the terminal category is going to give me this endomorphism monad of little t here, which has this formula here, which maybe you haven't seen before, but it's a monad, that's well known. Okay, I promise I'm also going to talk a bit about codensity monads. And the story here is simple. So a codensity monad is a special case of this push forward construction. And it's precisely when you extend the identity monad on the domain. So actually, secretly, all of those two examples I mentioned earlier were examples of codensity monads because I was extending the identity monad. Okay, now why do I talk about codensity monads? It's because they're a bit more famous than these this push forward construction, and there's more about them in the literature. So I can tell you about some interesting examples of those. So here's the most famous one, I want to say, which is if I take the inclusion functor from the category of finite sets of the sets, I take its codensity monad, that's going to give me the ultrafilter monad, which was briefly mentioned in the last talk. That's the monad whose algebras are compact Hampshire space. And so that's a really surprising example, because nowhere here is there any mention of topology or anything. I just know what a finite set, and what a set is. I have this functor. I take this categorical construction, and magically I get compact Hausdorff spaces out. So this is a family of examples that have to do with topology. The next one is maybe sort of if I linearize this example. So now I take finite dimensional k vector spaces and include that into the category of all k vector spaces. Then the codensity monad of that functor is the double dualization monad, where you send the vector space to its double dual. I didn't write what its algebras are, but they are something that deserves to be called linearly compact vector spaces, and they also have. So you can start to see the pattern here. One last example, again, of like including finite looking things into all things, is if I take the inclusion of finite groups into groups, I take its codensity monad, then that monad is the profinite completion monad of group, whose algebras are profinite groups. And those are, again, sort of topological groups that are limits of finite groups. So somehow it seems that this codensity business magically makes topology appear in some sense whenever we consider finite things into more things. Okay, so before I go into the example I want to talk about today, let me mention one universal property that this push forward has, which gives us some nice intuition about what this push forward monad is. So back when I defined it, I defined G star T as a right-hand extension, which meant that I had that natural transformation filling in the square. I can use that natural transformation to cook up a functor from the category of algebras of my original monad to the category of algebras of the new monad. Now, of course, these are monads of different categories. So the way that they're compatible is like as is squared %. So the underlying the object of the image of this functor is going to be G of the underlying object in C. So this allows me to define this functor K, and this diagram allows me to see it as a functor in categories over T. And the universal property is going to have to do with this sort of functor that takes a monad and produces its category of algebras. So this is a well-known functor, right? You have a monad on D. How do I produce a category living over D? Well, I take its algebras. And so, okay, the universal property is that this functor K that I defined here is a universal arrow from this bottom composite to the functor out. And so this, okay, let me say this more explicitly, because maybe this note the terminology of universal arrow is not so common these days. So what that means is the maps of monads from another monad on DS to this push forward monad are in bijection with arrows over D between these two. And that bijection is given by that old function, okay? But okay, so we could spend a minute trying to unpack what this means. The real, like, sort of one sentence answer is that G, the forgetful functor from the category of algebras of the push forward monad is the universal monadic replacement of this GUT here. Because sort of anytime I can map out of this functor to a functor that's monadic over D, that corresponds to a map of monads. So one quick corollary from this is if in this last sentence I take G to be actually GUT and T to be the identity, then this last part here stays the same because G is now that, and EUT, E of the identity is just the identity. So that stays the same, but this changes. And so actually what we get is that this push forward monad is actually the codensity monad of GUT here. So not only are codensity monads a special case of push forward monads, but actually all push forward ones can be. Okay, and then one last thing before I start with the examples is some functionality properties of this construction. So this G star T depends on this the existence of the right-hand extension. Let's assume for now that it exists for all monads on C. Then we get a functor G star from monads on C to monads on T. This is, for example, the case if C is small and D is so complete. And then one last little thing is that I could ask what happens when I push forward once and then twice, or all in one go. And it actually doesn't matter as long as one of the two functors, well, either H preserves limits or G is the right. And actually, there's examples where those are not satisfied, where this is missing. So, okay. So now let's look into some examples. So the most famous example of a condensed monad was that finite sets into sets. So let's see what happens if instead of pushing forward the identity, I push forward some other monads in finite sets. So here are the monads that I'm going to push forward. First one's going to be, so actually, before I say that, they're all going to be restrictions of monads on set. So let me introduce the monads on set, which are very well known. This one is, if I have a finite set E, I can consider the plus E monad, whose algebras are pointed sets. If I have a finite monad N, I can consider the writer monad here, which is multiplied by the monoid, whose algebras are left N sets. And then the last one's going to be the covariant power set functor, whose algebras are complete lattices. So all of these, you'll notice, if I plug in a finite set, I get a finite set back. So they all restrict to monads on finite set. And I'm just going to give those the same name, except having this declaration of the F. Okay. So what happens if I try to take these restricted monads on finite sets and extend them back to sets? Well, two clues as to what may happen are in this slide. The first one is, well, the unit of a monad is always a map from the identity monad to the monad itself. So because finite set is small and set is complete, I can use that functoriality result I mentioned. And it's going to give me a map from the extension of the unit to the extension of the monad. But of course, the extension of the unit, the identity, is the ultrafilter monad, which is the one for compact Hutton spaces. So I'm going to get a map from the ultrafilter monad to the extension of each of these TF. The other clue is that because TF is a restriction of already monad on set, I can draw the square and put the monad on set on the right-hand side, and I have an equality in the middle. So that's going to give me a map from the monad T to the extension of this restriction. And intuitively, what this is telling us is that whatever the algebras for the extended monads are, they're going to have an underlying T algebra structure, and they're also going to have a compact half-sphere topology. But we have to understand in which way these two structures combined. So the first two cases of pointed sets and left M sets are particularly simple. So it boils down to the fact that the ultrafilter monad preserves finite coproducts. I'm not going to prove that, but it's not a hard thing. And moreover, if you're careful and you look at that isomorphism, you'll see that you actually get distributive laws between these monads. So these are the distributive laws of the previous talk. And well, that means that UPE and UAM are monads in full right-on sets, and their algebras are E-pointed compact Hutton spaces and compact Hausdorff spaces with a continuous left M action. So actually, already we're seeing that whatever these monads are, their algebras fit the bill for the algebras of the extended monad. And indeed, that's the case. The extension of this add plus E monad on finite sets to all sets is this composite monad here, and the extension of the times M monad on finite sets is this monad here. I think I'm going to skip the proof for interest of time. And okay, so quickly for this other one, we're also talking about the power set monad, which is a finite set. There is a well-known monad on set that already restricts to finite sets, and that's the filter monad. And I guess no surprises here again. The extension of the power set monad from finite sets to all sets is this filter monad. And a good clue for that would be if we look up what the algebras are. The algebras for the filter monad are continuous lattices, which are a certain kind of complete lattices that have a compatible compact topology. So they do combine those two. So in general, I guess we've seen that with this functor of the inclusion of finite sets into sets, whenever we extend a monad on finite sets, we get sort of the equivalent compact Hausdorff variant of that monad on all sets. Okay, and then for the last, I want to talk about this interesting codensity monad, which is of the inclusion of fields into rings. So I'm gonna reuse the notation I because it's an inclusion. And I'm gonna call K its codensity monad. So why I'm interested in this one is because I is field is one of the first examples that you meet of a category that's not monadic over set for many reasons. One of like an easy one is field doesn't have products. So I'm interested in looking at this codensity monad because its algebras are going to give me sort of the monadic replacement of the category of fields over set. Okay, so let's dive in. So this monad K, I can use like the formula for the right-hand extension. It's going to be given by this. It's going to be indexed by maps from the ring R to any field K and the limit of K. Now, one key property here is that whenever I have a map from a ring to a field, I can take its kernel. That's going to give me a prime ideal. I can mod by that prime ideal, and I can then take the field of fractions, and it's gonna give me a factorization of that original map through this field, who is the field of fractions of a quotient of the ring. And actually, that prime ideal is unique. It only works if you take the kernel of the map. What that means at the end of the day is that this diagram that we're indexing on has sort of disconnected components, and each of those components has an initial object. So when I take the limit, I'm actually just going to get a product. And that product is this one right down here. So I'm going to take all prime ideals of the ring R. This is the spectrum of the ring, set of all prime ideals. I'm going to take the fraction field of R mod. So let's quickly see what this monad is doing. So first of all, the unit of the monad is going to be a map from R to this product. And I like to say that it embodies the, philosophy or the spirit of algebraic geometry, because it takes an element of the ring and it produces an element of this product. But if you look at it closely, these are just sort of dependent functions on the spectrum of the ring. And that's what algebraic geometry is like to think about. To understand the multiplication, I'd have to know what the prime ideals of this product are, but it turns out that the prime ideals of a product of field are easy to understand, and they sort of they correspond actually to ultrafilters on the index set. So somehow ultrafilters creeping again here. With that in mind, I can, I'm not telling you explicitly, but the multiplication actually only depends on some of those components of this big product K squared R, and they are exactly those components that correspond to principal ultra. Okay, let's try to guess what the K algebras would be. So this is meant to be like the replacement of the category of fields. Indeed, I have a functor from fields to this replacement, because that functor came from the first section. It's going to tell me that every field is a K algebra. Not only that, but because a ring is complete, any sort of category of algebras over a monad over a complete category is itself complete. So I'm going to have fields in this category, and I'm also going to have limits of fields. Now, field has equalizers, but it doesn't have products, as I said earlier. But it turns out that this is all it's missing to become monadic over set. And so here's sort of the punchline is that the category of K algebras is isomorphic to the category of products of fields. And this is sort of the free product completion of the category. But why stop there? I can then look at that monad K on ring and try to push it forward down to set. In fact, what I'm going to get, because this thing I'm pushing forward along is a right-hand ring, I'm just going to get the codensity monad of the composite of like sort of the function from field to set. And the very surprising thing here is, well, I guess this is a preliminary proposition, but you can see where this is going. This functor here preserves reflective co-equalizers, and I think I forgot to say, and this category has them. So no surprises if you can guess what I'm going to say next. That functor is actually monadic by the crude monadicity theorem. And we get this very surprising fact that the free product completion of the category of fields is monadic over set. even though field is clearly. And as I was hinting, this tells us that the smallest sort of algebraic theory containing theory of fields is the theory of products. And just to end here, yeah, some remarks about this theory. So it's not finitary, it's infinitary, basically because we have these big products lurking in the background. And it has some really interesting operations. For example, there's an n-ary operation that vanishes on all fields that have fewer than n algebraically independent elements. So it really knows quite a bit about fields themselves, even though it can't just accommodate fields, but it has to leave room for all the products. Yeah, okay, I think that's everything I wanted to say. Thank you for your attention.
What does it say?
Somebody raised their hand.
Oh, yes. You might be, yeah. What's the question? Or let me read it somewhere.
Do I have to do something?
I think we should talk. Well, the thing I was going to say, and I was hoping to get lots of Nathaniel, was that your discussion of fields reminds me of the work of the EDS, and Nathaniel is the modern expert on that.
Well, curious say.
Yeah. People cannot mute, so Nathaniel, if you'd like to unmute, you should be able to. Oh wait, maybe we can't hear them. No, we're making sound. Oh, you can mute. Go for it.
Hello, can you hear me?
Yes.
Very quietly.
Yeah, try again.
Can you hear me now?
I can't.
I can go more. No, I can't. That's as loud as we can go.
Okay. Hopefully it's loud enough to hear. Well, first of all, thank you for the talks. That's very interesting. I was wondering whether there's some relationship between these push forwards and distributive laws, because it sort of looks like when, say, G is monadic, then this looks a bit like a lifting of a monad. And so I was wondering, is there some sort of generalization of distributive law that captures these push forwards or something like this?
So I guess I have two answers to that. We've seen in some cases, for example, for finite sets, the push forwards did give us a distributive law between the original functor and the ultrafilter functor, but that seems to be a quite rare case. I think what you're hinting about though is if you just look at the sort of the right-hand extension diagram, if I say took G to be a monad itself, then and I had a distributive law of G over T, then I'd want to put T here and look at that natural transformation, right? And all I have to say there is that it doesn't quite capture the whole theory stuff about distributive laws, because this functor G here, I'm only using it as a functor and not as a monad. So it gives me a map of monads from sort of the monad T here to the extension to the push forward if the functor G has a distributive law over the monad or the other way around. But it forgets that one of them is a monad essentially.
So I guess just to quickly clarify, I was thinking of the case where G is a monadic functor, so the forgetful functor from the
Oh, okay, sorry. Well, if G is a monadic functor, then you're just going to get sort of it is a right adjoint, right? So the push forward is just going to be the monad given by the adjunction on the monad. So I guess I haven't thought about in that case if there's sort of any distributive law between the original monad and this extension, but I could look into that. Thanks.
Thank you.
I have quite a vague question, unfortunately. So thanks for the original motivation of this junction and pushing forward the monad on the right hand.
Yeah.
If I'm not mistaken, when it's a reflective junction, you actually do the opposites. So you pre-compose with the right adjoint, but the left adjoint
on the front. And then obviously in that case, where it's a reflective instruction, you're kind of it's nice small. So you have a fully faithful functor. And all of the examples you talked about had fully faithful functors as well. So I was wondering how this construction fits in with what you're talking about. Whether the full faithfulness is very important for what's coming.
I haven't considered that very well, but I do know that if, say, I think it doesn't matter very much that it's fully faithful, because whenever you have a functor g here, I could take the sort of limit completion of c and take the sort of the functor that induces from the limit completion to d if d is complete. That is not probably going to be faithful or full, and still has the same push forward. I couldn't say, but I can look into that too. Yeah. Don't know. I also looked into like pushing forward distributive laws. I don't think you can do that, but I guess with strengths I haven't checked.
So you had some pro completions. You had compact household spaces and finite groups. Now that's slightly different, isn't it? Because pro finite groups are they not totally disconnected?
Yeah, I think so.
Whereas compact houses the
Yeah.
So there seems to be a bit. I know there's a bit in chapter 6, I think, of Stone spaces by Peter Thompson about some things that work and don't work with pro completions.
Interesting.
You might like to look at that. Any more comments, or we think available here.
And we also can open the back doors to go outside, although I think the weather has decreased again. You can go outside if you want. So now he's got upstairs. People haven't made it yet. No, it's fine. Golden 85. I tried it. Still not good. Yeah. It's interesting though.
Yeah, I think it's only carrying the 2 degrees. Just in case. I think you don't like it. We have like a small number of series. Yeah. Small series. I hope you have good. One of them is the ideas. So you use that. If everyone is nice, so they was the I was one. Yeah.
I have an example of one. So there's.
Oh, the breed is nice. I'm very sorry. Well, I like your mic hold now. I feel like I have Like I have seen. Not really like my brothers and all, but yeah, sort of halfway through it.
Yes, it's always difficult to tell, like,
Session, the streams, we have to set this session thing. No, but I want to have the live stream stop in each session. We have separate videos for each session. Also, think how long the video will be if it's they can say here. I will mute actually. Yeah.